you about the J bolts. Okay, Hamza, let me know if you can see the slides. Hamza. Okay. Okay, first of all, if you see this picture, okay, so it means that, for example, this is the arrangement of placement of sheets. So this is the width and this is the length. And actually, this end lab, this is supposed to be connected with the purlin because purlin they are running in this direction, transversal direction, okay? And in this direction, the sheets they are supposed to connect with each other. So you have to understand. For example, here you can see these are the lot of bolts. So these bolts which are provided in this direction, so in the downward direction they may be J bolts. They are J bolts and they are connecting the sheets with the purlin. Anyhow, for example, you can say that there is the one purlin along this line and there is a one purlin along this line. So code says that we're supposed to connect the side lab along this length also. So along this, so we are connecting the side lab with ordinary bolts, and along the perpendicular direction of the truss, we are connecting with the purlin. So these are the, for example, some guidelines given by the code. So side lab 1.5 corrugation with fastener placed at a maximum spacing of 300 millimeter in perpendicular direction. So in perpendicular direction, side lab is to be connected with the bolt whose spacing should not be more than 300 millimeter. So again, which is the side lab? So this is the side lab, this one. So he says that along this length, we should connect the side lab with the ordinary bolt whose spacing should not be more than 300 millimeter or 1 feet. For example, here you will have the better idea. So in this direction, we are connecting with the purlin. So they can also be evenly divided. So along the also purlin direction, we can also maintain this distance 200 millimeter. So any distance less than 200 millimeter can be used. So that is not related with the strength criteria. And further, maybe there was also in the next slide. So minimum end lab. Uh, so for the end lab, the fastener spacing, minimum end lab fastener are to be provided not less than every third corrugation over each purlin. So sorry, end lab is provided along the purlin and side lab is provided along the direction. So here, let me discuss again. So this is the end of the sheet. So end lab is connected with this purlin. So he says that we need to provide the uh, fastener or the J bolt at each which corrugation mentioned here at every third corrugation. So at third corrugation we need to provide the J bolt. So third corrugation mean that 1, 2, 3. So you can see that 1, 2, 3. So every third corrugation at the top of the corrugation they have provided the bolt. So 1, 2, 3. So it means that what will be the distance between you can say that two bolt J bolts, because one corrugation is equal to around 75. So you can say that side lab is 1.5 corrugation. 1.5 corrugation is 115. So the 3 corrugation will be equal to 230. So twice of this distance will become the 3 time of the corrugation, because one corrugation is equal to the 1 time of the pitch value. So you can say that 75 multiplied by 3 should be the spacing of the J boards along this direction at each third corrugation. So which is the around 225. And along this direction means along there. To cover the side lab, so along the length of the sheet direction, what should be the spacing of the ordinary bolt? That is 300 millimeter. So that is given. So you can directly write down the same value, or in the summary you can simply write that the side lab is closed with us with ordinary bolt with spacing not more than 300 millimeter. So what you can do, you can divide the total length. For example, here, the example that we have solved. So which was the example? Yes. So here we have computed the length. So there was the length that we have computed. Yes, L1. So what you can do, you can convert this length into, for example, we are using 3.25 millimeter. Okay. So you can divide this by 300. For example, if I divide this value 3.087, 3087 divided by 300. 300 millimeter is this spacing. So I'm getting the answer 10.29. So if you divide this value 3087 millimeter by 300 millimeter, which is the spacing of the ordinary bolt to connect the side lab along the length, the answer is coming out to be 10.29. But I will round this 10.29 to the upper side 11. So it means that I need to provide the 11 bolt. Now I will divide this value by the rounded value 11. So the answer will be 3087 divided by 11. So answer is coming out to be 280. So end will side lab will be connected with a board of spacing 280 millimeter that I have computed by rounding the board's value. So similarly, along the along the length of the purlin, ant lab should be connected with at each corrugation at 1/3 corrugation. So we need to provide the J board. So you can directly write this command. So that's why we are having is 200, 219, maybe that is a actual distance at third corrugation. So this is equal to, I can see that 3 multiplied by around 75. So because the answer is 225, but actual pitch is not 75, actual pitch is different. So that's why answer is 219. So where is the, yes, actual pitch is 73. So if you are multiplying 73 into 3, so you are having a distance between three corrugations, 73 into 3. So answer is coming out to be exactly 219. Exact answer is 219. So let me this value. So here I'm multiplying 3. So corresponding to each, let me write also corresponding to each third corrugation. So an ordinary bolt to cover the side lab maximum spacing should be 300 millimeter. So I have computed this value as a 280. So this value should always be less than 300, or you can simply write the answer same like this in the examination. You can copy this statement, but the philosophy I have already explained. So Hamza, have you got the answer? Hamza, please let me know. Okay, good. Okay, now let me start the today's lecture. So we were discussing the design of the welded connection. So last time we have discussed the example for the connection design of tension member or a stress reversal member where the tensile forces are more. Now we are going to discuss another example where we need to design the weld for a compression member or a stress reversal member where the compressive forces are larger than the tensile force. So let me start the recording also. So, Bismillahirrahmanirrahim. Again, today, inshallah, we are going to study the example where we will learn that how we can design the welded connection for a compression member or for a stress reversal member where the factor tensile forces are more than compressive forces. It means that design criteria for this welded connection design will be the compressive forces. So first of all, we need to understand the what type of the data is given. So in the design data, design welded connection for the truss compression member as shown in the figure using E70 electrode. So E70 electrode mean that given a special restriction by the designer or by the architect or the planner. So we cannot keep any, this restriction is only with L1 or L2, not with L3. So maximum length of the weld means the length of the weld along the length of the member should not be more than 150. So this member is subjected to a compressive force of 600 kilonewton, that is the factor force. So this is the double angle. Double angle 102 into 102, equal leg, both dimension of the both leg is 102 millimeter, and the thickness of the angle section is 9.5. So area of the one angle is given as a 1850, and the length of this member is 1.5. So anyhow, if you are given the designation, standard designation of the section, you can also check the its properties or geometric properties from LRFD manual. For example, if you are opening the page number, I guess 56, sorry, 58. So on page number 58, in this second group, so you can write down the geometric properties of this section corresponding to single section. So area of single section angle is 1850, and we need the y value. Why we need the y value? Because in the angle section, the centroidal axis is not perfectly in the center. So in order to compute length of the weld L2 and L1, we need the y value for centroidal location with along the y axis. So this y value, again from the same table, let me open the table. That will be more appropriate. So that is the page number, I guess, 58. Because many students they struggle that where I am getting all these values. So let me rotate it. So yes, I am exactly on page number 58. I have to consult. So this is page number 58. Yes. And our section is 102 into 102 into 9.5. So area of this single section is 1850. So we need the Rx value 31.2, Y value is 29.0. Here you can also check what is the Y. This is the centroidal location along the Y axis, and we also need the radius of gyration about Y axis. So only these values may be required. So yes, we are now writing these values over here. So actually, you don't need to compute the RY actual. That is a wastage of time. Why? Because we are having equal leg angle section, the built up. So for the equal leg built up angle section, Rx value of the built up section will always be less than Ry. And you know that Rx value for the built up section is equal to the Rx value of the single section. So since our given section angle section is having the Rx value and Ry value for single angle same, just like C. So its Rx value is 31.2 and Ry is also 31.2. So when we are making a built-up section, so Rx value remains same, so Ry value increase. It means that for the built-up section, Ry value will be more than uh, as compared to the single angle value, but Rx value uh, of the built-up section will be same as of the single section. So it means that we already know that for a built up equal lag built up section, Rx minimum will be Rx value. So you don't need to compute those. You can simply write down this sentence. For equal lag built up section, Rx value will always be R minimum. But anyhow, if you want to check, you may compute this value, actual value, or you can compute by the approximate formula which are given on the page number 100. So actually what we are doing, we are doing actually, we need to compute the, we need to use this formula to compute the length of the weld. So the length of the weld is equal to the design weld force divided by weld value. And this FU force, actually this is lesser value out of 50% capacity of the member and a factored force which is acting in the member. So actually we need to determine the capacity also. So the capacity of the compression member is the base upon slenderness ratio. So we are given the effective length because that member is belong to the truss member here. Length is given as a 1.5. So this is the truss member. So K value is equal to 1. So slenderness ratio will be 48. So if the slenderness ratio is 48, corresponding to R 48, you can check what is the phi CFCR value, and phi CFCR value you can consult from the page number 106. So let me rotate it again. Yes, from the page number 105, I guess. So what was our slenderness ratio? So it was 48. So corresponding to 48, we need to check what is the critical stress at which the column may buckle. So that value is 199.12 for 830/60. So corresponding to slenderness ratio 48, while CFCR value is 199.13. So that we have fixed. So now the capacity 50. So we are directly computing the 50% capacity. So the compressive capacity is equal to phi CFCR value into the gross area of two angles because that is a built-up section. So the 50%, we have already computed the 50% capacity divided by half. So the 50% capacity is 368.4 kilonewton. So design weld force for two angles is the larger value out of PU, which is 600, that's which is given here. Factored applied compressive force for 50% capacity. So factored force is more, 600. So FU will be 600. But in design guideline, I already told you that if we are given the built-up section or double angle, we design the weld for single angle, and the same weld will be provided on the both sides. So what we will do, we will divide the FU value 600 by 2. So we will determine the design weld force for single angle, which is 300. Okay, second is we have got the FU value. Now we need to determine the weld value. So actually for the weld value, it is the strength of a unit weld which is either based upon base metal or weld strength. So for the weld value, we are computing a weld of unit size, length is equal to 1 millimeter, but we need to fix the thickness of the weld. So for the thickness of the weld, actually we need to know that which two plates we are connecting. So we need to connect this angle, the leg, and leg dimension is 9.5 with the gusset plate whose thickness is equal to 10 millimeter. So we are connecting two plates. So plate which is thinner, we refer that plate as a TP1. So TP1 will be 9.5, which is the angle, thickness of the angle, and TP2 is the thickness of the larger plate, which is our gusset plate. Then what you supposed to do based upon TP1 and TP2? First of all, we are determining the TW minimum. So TW minimum, these tables are also provided in LRFD manual. If you are opening page number 86, so let me open the page number 86. So this is the page number 87. Yes, this one. So TW minimum is based upon TP1. So our TP1 is between 6 and 13 millimeter. TP1 is 9.5. So our TW minimum will be 5 millimeter. So that we have written over here. So TW minimum is 5 millimeter because TP1 is between 9 to 13 millimeter. Similarly, we will compute TW maximum, and again you need to consult LRFD manual. This is for the groove weld. We will not use this, but we are going to use this fillet weld. So along the edges of material, 6 millimeter or more in thickness. If TP1 is more than 6 millimeter, then TW maximum is computed by this formula. If TP1 is less than or equal to 6 millimeter, then the maximum thickness of the weld cannot be more than TP1. So our TP1 is 9.5. So to determine the TW maximum, we're supposed to use this formula TP1 minus 2. So again, you need to know that which formula you need to consult. So all the formula design guidelines, they are available in LRFD manual. So I'm consulting the page number 86. So TW maximum will be TP1. So let me write as a TP1 value minus 2, which is 7.5. And I have already told you that the T optimum is always 6 millimeter, sorry, 8 millimeter. So what is the T optimum? T optimum is the maximum thickness of the weld that can be provided in a single layer or single part, which is 8 millimeter. So we are having these three thicknesses of the weld. So I told you that when we determine three thicknesses, we arrange them in ascending or descending order. So middle value may be used as a thickness of the weld. So middle value is 7.5. So TW adopted is 7.5. You can round to the nearest integer value. So here we have rounded to the upper side 8 millimeter. If you want, you can also round to the 7 millimeter. That is not going to make difference, because if you are using the lesser thickness, length of the weld required will be more. But if you are using the higher thickness, then we require less thickness of the weld. So in this example, we have rounded to the upper side. Why? Because we want to reduce the weld length, because we are given the maximum limitation for the length of the weld. So that's why I have rounded the T adopted to the upper side 8 millimeter. But again, that cannot be more than T optimum. But if you want, you can use this value also as a 7 millimeter. So that will not make any difference. So you are getting the full marks for the design problem. Okay, next is that we need to determine the weld value. which is the lesser value out of the weld strength and base metal. So first value is the weld value based upon the weld strength, shear strength of the weld, which is considered as a 60% of the normal strength. We are given E70 electrode, and for E70 electrode, so for E70 electrode, Fe value is 495. If you are dividing this 70 by 40 KSI, sorry, 0.145 KSI, and into the area of the weld, effective throat into the length of the weld. Effective throat is considered as a 0.707 time of the thickness of the weld. So in this equation, we are substituting the values. So there is the one error. So in this, let me correct one mistake. So the mistake is that, so I haven't multiplied this by the pi value. Similarly here, reduction factor. So this value will be 0.75. Anyhow, the answers, they are correct. So 0.75 is the capacity reduction factor for weld failure, which is the rupture. So 0.77 thickness of the weld, we have computed 8, and for the weld value, we always consider the length of the weld as a 1 millimeter. So if we are computing the answer from here, so we will get the answer as a 1.26 kilonewton per meter. We have divided it by 1000 to convert the answer into kilonewton. So here again I have error, so I will correct it again. So that, because all the dimensions are in millimeter, so that is kilonewton per millimeter. Because the unit length we are using 1 millimeter and thickness of the weld are also in millimeter. So we are dividing the equation only by 1000 to convert the Newton into kilonewton. So the units will be kilonewton per millimeter. Similarly, the weld value based upon the base metal will be phi value, shear strength of the base metal, which is equal to 60% of ultimate strength. Because base metal will fade due to rupture, so that's why we are using the ultimate strength. So, and area of the plate, so area of the plate will be TP1. Always use the lesser thickness of the plate into the length of the weld. So plate will be torn along the weld direction. 0.75 is the phi value and 0.6 Fu is the shear strength of the base metal. So Fu value for 836 steel we are using for the base metal for the angle section. So 0.6 is the factor to convert the normal strength into the shear strength. 9.5 is TP1, and the length of the weld we are using as a 1, and we are dividing it by 1000 to convert the answer in kilonewton per millimeter. So we are having two weld value. Based upon the weld failure, we are having the answer 1.26, and based upon the base metal failure, we are having the answer higher, 1.71. So lesser value is 1.26. It means that the connection will be failed due to the failure of the welding. So the lesser value out of these two will be our weld value. So that value is the based upon net weld. So simply we are calling as a weld value. So our weld value is this one, 1.26. Now we already determine FU value, design weld force, which will be transferred from the one section to the other plate or vice versa. So length of the weld will be equal to total force divided by 1.26. So if the total force is acting 300 and force is resisted by a weld of unit length is 1.26, so we can determine that how much length of the weld is required, which is 238 millimeters. So first we have already derived the formula. So first of all, we will consider that we are not going to provide the L3 and we are just computing the weld value L1 and L2. So first we will provide the weld L1, L2 without L3. So we are having two formula that we have already derived. Maybe we have discussed. Where was the derivation? Yes, here. So we have determined the formula for L1 and L2. So these are the formula with if we are using L3. But if we are not using L3, so this factor will become equal to 0. This one and this one. And here, this is the configuration. So this is a double angle. So we are only designing for the single angle, and then we will provide the same weld on the other side. So I will always recommend always determine the L1 value first, not L2. Because if you are determining the L2 value first, then you round the L2 value and determine the L1. So the total weld may be on the upper side. But anyhow, what I am recommending that always determine the L1 value first by this expression. So we supposed to have minus L3 by 2, but first we are assuming that L3 is equal to 0. So if we are determining the L1, L1 will be equal to total length of the weld d minus y over d. So 238 is the total length of the weld. D is the total depth of this section, which is 102, which is given. And y value we have already determined from our reference manual, which is 29. After substituting the value, so d is 102, d minus y 29 is the what I can say that the centroidal location divided by d. So the L1 value is coming out to be 170 millimeters. So if we are computing L2 value, so total length of the weld will be equal to L1 plus L2. Or in other words, L2 will be equal to length of the weld minus L1. So 238 minus 170, so L2 will be equal to 68. But anyhow, L maximum we are given in this statement is 150. So, but we have computed this L1 value as a 170, which is coming out to be more than 150. So how we can reduce this value? So in order to reduce this value, now we will provide the L3. So we will provide L3. If we are providing L3, so length of the weld L1 and L2 will be reduced. So L3, the length of L3 we know, because L3 is always provided along the full depth. So the L3 will be equal to D value, which is 102. So L1 is more than 150 and L3 is, so we are going to use the L3 value, which is 102. So L1 will be by this formula. So D by 2, or you can say that that is the L3 by 2. So L3 will be equal to D value. So you may either write L3 or D by 2. Please mute your mic, please, dear student. So here L1 will be this formula. You have already computed this value and minus L3 by 2. You have already derived this formula. So you can subtract d by 2 from already computed L1 value because we have already computed the value by this formula, so which was 170. Just see here, we have already computed this value which was 170. So 170 minus L3 by 2. So L3 is equal to D value. So updated L1 value will come out to be 119. So we are rounding this value into the multiple of 5 millimeter on the upper side because weld is always provided in a multiple of 5 millimeter in length direction. So that is 120. So if you are computing L2 value by this formula, so this value you have already computed 68 minus d by 2. So this is 17. Now you will check the this value with ACI formula L1 and so the LW minimum and LW maximum. And I believe that these values LW minimum is equal to 4 times of thickness of the weld and LW maximum is 170, so 30 times of weld. So in our given case, so that value is equal to 150 for given case. Okay, so we can, so in our uh, given is this one. So if we are provided, then we are not going to the LW maximum limit for the code. So LW maximum for our given case is 150 millimeter. Again, if you don't memorize this value, so these values are also given in LRFD manual. Just see here on the page number 86, LW minimum is 4 times of thickness of the weld and maximum is 30 times. So effective length of the any segment for intermittent weld is, we are having this limit for intermittent 4 times thickness of the weld or 38. But for a single weld with one length, for a single weld, LW minimum is 4 times of thickness of the weld. So 4 times of thickness of the weld is 32 and LW maximum is 150 in our case. So L1 is 120. So this 120 is less than 150 and more than LW minimum. So we will use the L1 as it. But L2 value is 17. So this value is coming out to be less than LW minimum. So if the length of the weld is less than minimum length of the weld, so we will provide the weld equal to LW minimum. So we are using the L2 value equal to LW minimum because we cannot provide the length of the weld less than LW minimum. So why the reason? Because when we provide the length of the weld, so the starting or the end portion of the weld, it may have some bubble. So it means that the strength provided by the weld is less than the total length. So L2 will be 32, which is equal to LW minimum. But again, we will round this value to the multiple of 5 millimeter on the upper side. So L1 is equal to 120, and L2 will be equal to 35, and L3 will be equal to 102. That will not be rounded because weld L3 will be equal to depth. And then at the end, you need to show the weld on a neat sketch like this, and by showing proper standard designations. So you will sketch this, and L1 is provided on the thickness section. So this L1 is equal to, sorry, here I have reversed it, but I will correct it quickly. So this weld is supposed to be 102, sorry, 120. So this weld is 120, but this weld is 35. Yes. So L1 is provided. So gutter plate will start at the edge. So this simply indicates the thickness of the weld is 8 millimeter, and the length of the weld is 120. And I have shown this triangle on the both sides. It means that we're supposed to provide this weld on the both sides, because on the other side of the plate also, because we are having double angle. And this weld indication show that we need to provide a weld whose thickness is 8 millimeter and the length is equal to 35, and we need to provide this weld on the both side of this plate. This is L3 whose thickness is 8 millimeter and the length is 102, and we need to provide this weld on the both sides because we are having double angle. Again, why on the both sides? Because we designed this, we were having double angle. We designed the weld for single angle. So the same weld will be provided on the other side also. This is the case. This. So we are providing the weld here. So same weld is provided on the other side also. So that is the philosophy. So I told you that here the gutter plate will start from the edge of this weld, and this L1 it can be provided anywhere along this length, but it is better to place this L1 to closer to this edge. You can provide in the center, you can provide in the center also. That is not going to make any difference. So at the moment, if you are having any question from here, from the welded connection design, you can ask me the question. If you are not having any question, then I will move to the next topic. So you have already designed your weld. So what you are supposed to do now, you can start designing the welded connection for your truss member, and you can write down in a summary. So what you may do, so let me make a table. If I can explain you from the table, you can make a table for the welded connection design for your. So what must be in this table? I will delete the extra column if required. So this is not appropriate. Okay, you will make a table. For example, because you need to design the weld for your truss. So in the first column, you will write down the maybe member, and the next column you will write down the length, and here you will write down the designation. And for example, your member may be member number 1, member number 2. You have already given the designation. member number 3, and here you will write down the length in millimeter maybe, or meter, maybe 1.76, or maybe any value. Maybe you can write in meter or millimeter, that is up to you. And here in the designation, you are going to write whether this is the double angle or maybe single angle or whatsoever. 102 into 89, maybe into 9.5. This may be, and then here you will write down the depth, maybe d value, and d value maybe you can write in millimeter. And here you can write down its y value, and this y value you can pick from the table. So you are having d value in millimeter and d minus y, and further let me add some more column. So in layout I will go insert, so I will have to maybe here. So let me make this table bigger. So here you are going to compute the length of the weld. So that will be also a summary page also. So you can write, okay, no problem, FU value. FU value you will determine accordingly 50% capacity or the largest compressive or tensile force. And here you are going to compute L1 value, and here you are computing L2 value, and let me add one more column, and I'm reducing the and here if L3, if you have determined this value. So all these value will be in millimeter. So you can write down their units at the bottom, maybe just like I have written. Or what you may do, let me insert the row above, and just to make this concise, so you can write down the unit in the next row. And you can write down here. So here you can make the summary. So L3 may be 0. So actually, first of all, you need to design the weld for the heaviest member. Please remember that you need to design the weld for the heaviest member, and your R value, thickness of the weld will be fixed. So thickness of the weld, you are using constant value for the entire truss. So RW you are computing for the heaviest member. So you are computing the whatever is the member which is having the largest thickness or the largest force, you are going to determine the thickness of the weld value. So the thickness of the weld value will be constant for you. So it means that weld value will also be constant. So weld value will be constant for the entire truss, and that will be based upon the heaviest member. And then FU value, design weld force will be different for each member. That is either the factor tensile compressive force or 50% of the capacity. And accordingly, you are going to determine the L2, L1, and L3 value. So if you are having any confusion, please ask me the question. Then I will be going to on break maybe for 10 to 15 minutes. So yes, Udair, what is the question? Please quickly ask. Then I will go for the break.
सर एक जनरल क्वेश्चन पूछना था सर, ये जो हम हमारे पास एंगल सेक्शन होता है या डबल एंगल सेक्शन वगैरह, तो सर इसकी जो लॉन्गर लेग हम कनेक्ट करते हैं उसकी डायरेक्शन हम अपवर्ड रखते हैं या डाउनवर्ड रखते हैं?
ये देखो, मैंने आपको ना ये मेंबर की बताया था पहले, तो आई हैव ऑलरेडी एक्सप्लेन। तो उसमें ये है कि जो हमारा बॉटम कॉर्ड है उसमें, मैं अभी आपको दोबारा बता देता हूँ जस्ट क्विकली। ये देखो, ये जो टॉप कॉर्ड है, टॉप कॉर्ड में लॉन्गर लेग वी आर कीपिंग डाउनवर्ड, so we are keeping the horizontal length upward. Why? Because in this way we can easily connect the roof sheets. You understand me? But for the bottom chord, this is the bottom chord, we are keeping the vertical leg on upward and we are keeping the projected leg in the downward direction, so that they can easily be placed on foundation or some on columns. समझ लगी बात की? जो बॉटम कॉर्ड है,
यस
फॉर द
सर।
बॉटम कॉर्ड में थिकनेस डाउनवर्ड होगी और टॉप कॉर्ड में क्या होगी, वो अपवर्ड होगी, ठीक है। एंड
यस सर।
फॉर डायगोनल मेंबर वी कैन प्रोवाइड एनीवेयर इन एनी डायरेक्शन।
सर ये तो हमारे पास ट्रस में हो गया जब हमारे पास कंप्रेशन या टेंशन वगैरह है, लेकिन सर अगर पर्लिन डिजाइन हम एंगल से कर रहे हैं तो उसमें फिर जो है वो
नहीं, उसमें देखो, वो तो आपका क्वेश्चन ही नहीं बनना चाहिए। उसमें हमेशा जो है, क्योंकि हमने पर्लन के साथ रूफ शीट्स कनेक्ट करनी है, तो उसमें जो उसकी जो फ्लैट या प्रोजेक्टेड लैग है वो अपवर्ड होनी चाहिए। उसमें मैंने आपको अरेंजमेंट दिखाई भी थी, एक मिनट। और उसके एंगल को सीट करने के लिए, पर्लन के ऊपर रखने के लिए हम क्लीट एंगल यूज करते हैं। लेट मी शो यू इफ आई एम हैविंग नॉट हियर। So let me open the other slide. अब ये देखें आप, ये चैनल है, चैनल में आप समझे कि ये एंगल है, एंगल में ये होगा कि ये प्रोजेक्टेड लेग ये होगी और वर्टिकल लेग ये होगी, और ये नहीं होगा। इसको साथ सीट करने के लिए हम क्लीट एंगल लगाते हैं सारा। तो दिस इज द पर्लन। नो एक्चुअली ये टॉप कॉर्ड है, एक मेरे पिक्चर होगी मेरे पास यहाँ पे, अभी मैंने कहीं पे, यस दिस इज, ये है हमारी पर्लन की अरेंजमेंट। ये हमारा पर्लन है, सो विच इज एंगल। तो ये लेग जो है ये आपकी वर्टिकल है, ये डाउनवर्ड होगी, और ये जो हॉरिजॉन्टल लेग है दैट विल बी अपवर्ड, सो दैट अ रूफ शीट कैन बी कनेक्टेड। और ये जे बोल्ट जो है वो आपकी रूफ शीट को कनेक्ट करेगा। यहाँ पे हम जहाँ पर्लन के ऊपर जो सपोर्ट होती है वहाँ पे एक क्लीट एंगल लगाते हैं, ताकि ये जो एंगल है ये स्ट्रेट रहे। तो ये मैंने आपको उसकी एग्जाम्पल बताई थी। ठीक हो गया?
यस सर। सर वैसे इसका भी थोड़ा होता है इसमें कि फॉर एग्जांपल अगर हम फॉर एग्जांपल बीम डिजाइन करें तो उसमें टॉप पे कंप्रेशन आएगी, तो लोकल बगलिंग को जो है बचाने के लिए भी हम
नहीं
रख
नहीं
सकते
नहीं
हैं या
नहीं
नहीं?
नहीं, नो नो नो, एक्चुअली उसमें देखिए, मैंने आपको अभी, जब आप एग्जाम के बाद, ये छुट्टियों के बाद आएंगे ना, तो आपको साइकोमोटर असेसमेंट होगी, तो यू आर सपोज टू ड्रा द ड्राइंग शीट। So I will give you the detailed instruction. So when you are sketching the drawing sheet, so in drawing you will come to know that how you are going to place each member. So you will done properly. Anyhow, actually, if we are providing the, for example, I section or the channel section, so we are not having any issue regarding the placement. But whenever we are going to design the purlin as an angle section, so we are keeping this horizontal leg upward, because we need more flat surface to connect the roof sheet. Roof sheet cannot be placed on this lesser thickness. So roof sheet is only placed or it is connected with this horizontal leg. So just to support the purlin above the panel point at the truss, we are placing a cleat angle. So cleat angle, just this is the cleat angle, this one, whose thickness may be equal to the width of the section or maybe a little bit larger. So when you are going to sketch the drawing sheet after the break, maybe 2-3 weeks when you are visiting your university for psychomotor assessment. So I will give you the detailed instruction regarding this drawing sheet, and then when you are sketching the drawing sheet, then you will have the better idea how we are going to construct or fabricate our truss after designing. So if they, I will responding your question maybe after the break. So let's have the break for maybe 15 minutes. So time with me is 11:06. So I will be back around 11:20. Okay, please hold on. For your clarity, I am going to maybe open the last slide so that you can see that how I have get this table or shown this destination. So I will be back. So please hold on. Okay, CR, can you hear me? Class CR,
Yes, sir.
are you there?
Yes, sir.
Good. So let me start the new topic. Okay, can you see these slides, Sia?
Yes, sir.
Okay, good. Okay, Bismillah Rahman Rahim. Okay, dear students, we are going to start the new topics, and that is related with the connection design. And now here in this particular topic, we are going to study how we can design a fastener type of the connection. Fastener means riveted or bolted truss connection. So I'm just going to explain some salient feature of this fastener type of the connection. So first of all, we have to see that if we are going to design the fastener connection, rivet or bolted, then what are the forces which are acting in the connection and what are the possible failure? Because we want to avoid that type of failure. So design philosophy is the same. So we are going to compute the number of the fasteners required instead of the length of the weld. So the fastener connection will be designed again based upon the force. So you can say that the formula will be same that we have discussed. Which formula? This one. So you can say that I will copy over here. So in this fastener type of the connection, actually, instead of using this formula, we are going to use this formula, which is similar to the formula that we have used to design the length of the bed. So in this formula, some of the parameters, they are same. So actually, we are interested to compute the number of the fastener or number of the rivets required to safely transfer the force from the one member to the other member. So the number of the rivet is computed by the FU. FU force is the same that we have already determined for the welded connection design. So that is the largest factored force in the acting in the member or 50% capacity. So whichever is larger, that is the same. But But only thing is that we need to determine the RV value. So RV value is similar to the RW. So what was the RW value? RW was the weld value or the strength provided by a unit length of the weld. Similarly here, weld value will be replaced by another value which will be referred as a RV. So RV we are regarding as a rivet value. So rivet value mean that that is the force resisted by a single rivet or single fastener. So how much force a rivet can take before the failure is referred as a rivet value. So if we know the total force, for example, let's suppose that force may be 100, which may be transferred from the one member to the other member, and the rivet value is equal to 20. 20 mean that a force resisted by a single rivet to avoid failure is 20 kilonewton. Then how many rivets will be required? So Fu divided by Rv value. So it means that we require 5 number of the rivets to transfer the force from the one member to the other member. So why I'm explaining this? Because this rivet value, how we may compute, that is the point of interest here. So this rivet value is based upon type of stresses which are produced in a fastener or riveted type of the connection. So first of all, I will give you the idea about the stresses which are acting in a fastener type of the connection. So you may assume that we are having two plates. This plate is in the bottom and this plate is the top. For example, this plate is equal to this one plate and the top plate is this one. And these are subjected to tensile forces. They may be subjected to compressive forces. And we have to study different terminologies. So the total distance that we need to, the total thickness of the connection that we have to connect by the fastener or the rivet is called as a grip. So grip is equal to the thickness of combined thickness of two connecting plates. And then we are having the head of the fastener. In case of the rivet, we are having the head. In case of the bolt, we are having the head of the bolt on the one side and the nut on the other side. So the type of the stresses, if this plate tensile force is acting in this plate in the one direction and in the other tensile force is acting on the other direction, then we are having two type of stresses which may act here. Number one is the bearing. So bearing mean that these bearing stresses, they are acting opposite to the force direction. So if on this plate, force is acting on the other side, so the area surrounded by this rivet or this fastener, it is subjected to the high compressive stresses. So this area is bearing. So the length of this area can be considered, which is under bearing or compression is equal to the diameter of this fastener and the length is equal to the total thickness of the plate. So this area is under bearing. So it means that the tensile or the compressive force which is transferred from the one member to the other member through this bolt. So it is causing the bearing stresses which are compressive by nature on the one side. So if this force supposed to be compressive in this side, then this side will be under bearing. For example, if this force is acting on this side, then the bearing stresses are acting on the opposite side. So bearing stresses are acting in one plate. And similarly, due to the tensile force here, bearing stresses are acting on the opposite side. If this force is compressive, then the bearing stresses might be acting on this side. So the area which is under direct bearing, we can consider the thickness of that area is equal to the diameter and the length is equal to the length of the plate. And these are the bearing stress. Due to bearing stress, if these stresses are more than yield strength of this base metal or material, then the yielding will occur along this area and this hole will widen, and due to the widening of this hole, the plate will come outside the fastener. So this will cause the failure of the plate. If these bearing stresses are less than the yield strength of the material, then plate is safe against bearing. Then we may have other type of the failure, which is called the shear failure in the bolt. So this force and this force, they are same. These are the tensile force with reference to this plate, but with reference to this area, cross-section area of the bolt, they are causing the shear stress on this rivet. So if the shear stresses at the cross-section of the rivets, they are more than the shear strength of this rivet or this bolt, then the rupture or the failure, shear failure will occur in this. So it means that we may have two type of the failure. One is the bearing failure and one is the shear failure. So we need to compute that how we can avoid this failure, or how we can compute the shear strength of a single fastener and a bearing strength. So shear strength formula is quite simple, but again, this bearing strength or the bearing stress, these are the function of the edge distance. So what is the distance from the center of this river to the edge? That we are going to discuss in our upcoming slide. Again, I'm explaining that when in the fastener type of the connection, we may have two type of the stresses, number one bearing and number two shear stresses. And depending upon these stresses, we may have any type of the failure, maybe shear failure in the rivet or the bearing failure in the plate. Just like the failure of the base metal and the failure of the weld in case of the welded connection. So the bolt may be arbitrarily tightened called snug tight bolt, we have already discussed, or we may have high tension bolt. In high tension bolt mean that we are providing the pre-tensioning to the bolt by tightening. So distance between the two head after placement of the fasteners is called grip, just like I have mentioned over here. A bolt joint in which the slip resistance of the connection is also utilized is called the slip critical joint. Okay, how I can explain this? I will explain by this. So I told you that diameter of the hole is usually more than the diameter of the fastener. So we know that when you are computing the net area, so we are using D plus 3 into thickness. So D plus 3 actually is the diameter of the hole. So hole size is 3 millimeter more than the diameter. It means that if we are providing the tensile force, so there is a margin that due to this tensile force, this plate, it can slip in any direction by 3 millimeter. Because why 3 millimeter? Because size of the hole is more than the diameter. So if this plate can slip through this plate can slip along the diameter, so this is called slip critical. So it means that slip is allowed. But if we have tightened this bolt or the fastener by firm connection, or if the contact pressure is very high, then this plate cannot slip, because due to the tensile force or the because we have tightened this bolt by some pre-tensioning. So due to the very high contact pressure, even though the hole size is more, so this plate, it cannot slip. So it means that slip is prevented. So a snug tight connection is always having some slip, because we are not tightening the bolt by some specified pre-tensioning. So this is the connection which is where we are obtaining the tightness by the full effort of a single person. So it means that that's why for snug tight connection we always compute the modified slenderness ratio, because due to slippage So actual slenderness ratio may be more or the capacity will be less. So a board joint in which slip resistance of connection is also utilized is called slip critical. So there are different types of the boards available in the market, and depending upon the board dia, we can provide the pre-specified pre-tensioning. So we are having the diameter of the board available in millimeter. We are have M15 board. M15 means that diameter of that board or the rivet will be 15 mm. And if we are having M20 board, M20 board means that the nominal diameter will be 20 mm. So if we want to use a bolt of diameter 15 mm, so we need to punch a hole of 17 mm. So we are having a 2 millimeter margin of slip in this case. So this slip can be avoided if we are providing the pre-tensioning. So depending upon the strength of the bolt, so we are having two type of the bolts available. One is a 325M and other is 490M. So in this table, A is the chapter of ASTM which deal with the metals, and 325 is the ultimate strength of this bolt, and M indicate mild steel, and 490 indicate that M15 bolt whose diameter is 15 mm and ultimate strength is 490 megapascal. So if we are using M15 bolt of strength 325 or grade 325, so we need to provide a pre-tensioning by 80 kilonewton. Similarly, if we are using M25 bolt and if it is grade A325, then we need to provide a pre-tensioning equal to 225 megapascal. If we are using grade 490, ultimate strength is 490 megapascal, then we supposed to provide the pre-tensioning 282. And this table indicates the diameter of the hole that we need to punch to accommodate any particular nominal diameter of the hole. So next question arises that how we can check that we have provided this much pre-tensioning. So actually you can read out this slide yourself. So in hot driven rivet, we cannot control the pre-tensioning because after providing the rivets, so because the rivets they are in hot form, when they cool they shrink. So due to the shrinkage of the rivet, the pre-tensioning or the compressive forces are acting on the plates, which are holding the both plates together, and they are tightening the connection. But we cannot control the same tightening in all type of the riveted connection. So ASTM specification A502 deal with this type of the rivet and qualify these rivet are as a grade 1 and grade 2, grade 3 rivet. So we are having three type of rivet. I am checking the any table if it is available in LRFD manual. So that where the properties of this fasteners are given. So they may be given on page number 4 grade 3. So their properties, they are mentioned in this table, which you can consult on page number 88. So in this table, we are given in the first column type of the fastener, their tensile strength, 5 values strength reduction factor, and their shear strength. Shear strength, shearing strength in bearing type of the connection. Bearing type means where they are subjected to the shear forces. And 5B, strength reduction factor in shear. If we are using the A502 grade 1 hot driven rivet, so ultimate strength of this rivet is 310 megapascal and the shear strength is 172. And again, we need to multiply with the strength reduction factor 0.75 in tension and 0.75 in shear. So ASTM standard A502 for grade 2 and grade 3 type of the fastener. Grade 2, grade 3 mean that they are having the high tensile strength. So 414 is the tensile strength and shear strength is considered 228. So if in the example problem or in the examination, you are told that use the grade 2 or grade 3 hot driven rivet as per ASTM 502. So it means that you need to consider the shear strength of that type of rivet as 228 and ultimate strength as a 414. So you need to consult this table. So if you will check, ratio of this shear strength to the ultimate strength is considered as a 0.55, or it means that the shear strength is considered as 55% of the ultimate strength. So you can check also. So if you are dividing 172 by 310, you are having the answer 0.55. Similarly, also here. So if you are using bolt of 307, which are manufactured as per ASTM standard of 307, so its ultimate strength will be 310 and shear strength will be 188. So here you can check that shear strength is considered 55% of FU. So for a 325M bolt, FU is 825 megapascal when threaded are not excluded from shear plane. So if we are having A325M type of the bolt, A325M bolt which are manufactured as per ASTM standard A325M, so ultimate strength of this bolt is 825. But if we are using the bolts, so this bolt is having lesser area as the threaded portion. So it means that bolt will always fail at a portion where the cross section area is less. So the chances of failures are more at thread. Therefore, to consider the failure at the threads, so ultimate strength is considered as a 75% of the ultimate value. So we are considering ultimate strength of the bolt as a 75% of the ultimate strength of material, just to consider the failure at the thread. So FU is 620 megapascal, which is 0.75 of 825 megapascal due to the threads. If we no threads are available and this is a rivet, then FU value may be considered 825. And the shear strength is considered because even though we are having the bolt, so our thread area will be here in this side, but at this shear plane we will not have any thread. It means that if the shear failure occur in the bolt, it will always occur at the point or at the area where we are having no thread. So in that case, the shear strength will be considered 55% of the total FU. Total FU mean that here this 0.55 is the 55% of 825, not this value, because at the plane of shear, at the plane of maximum shear, so we are not having any threads. Similarly, at 490 mm, if tensile failure occurs, so in case of retention, ultimate strength is considered as a 75% of the ultimate strength. But in case of shear failure, so shear failure is considered as a 44% of this ultimate strength. But anyhow, you don't need to memorize this value. Corresponding to any given rivet or the bolt, you may consider the shear strength or the ultimate strength, tensile strength from here. So next question arises that in pre-tensioning, how we can indicate that we have provided this much pre-tensioning. So I will give you a simple example. Let's suppose we know the total length of this grip. Total length of the bolt will be the length between these two plates, which is equal to the grip. And let's suppose this is the length. So for all type of the material, let me explain by not here but here. So you can say that we know this formula. We know that the stress is equal to strain very simple for the strain supposed to be here. Yeah, this one strain into the modulus of elasticity. So stress is equal to strain into the modulus of elasticity. So E value for the steel is constant. So strain is equal to change in length. We have to pick delta value over original length. So if I want to produce a pre-tensioning, for example here, just like in this table we have discussed, which was the table? Yes, this one. If I'm using a 25M bolt, and it means that if this is a 325M bolt, so I need to provide a pre-tensioning of 225. So how I can provide this pre-tension 225? So it means that in this formula, if I want to produce this stress 225, so I'm substituting this value as a 225, and this E value of this steel I know as a 2 into exponent 5, 200,000 megapascal. And if I know this length, which is I am causing as a L grip, so length of the grip. So only unknown is the delta value. So delta value will be equal to so this delta will be equal to L grip divided by 225, the stress that I want to provide, and multiply by this E value just for your so I may also write this value like this, and here I will write this in terms as a F multiplied by E value. So this is the formula. Where will this formula go? Yes, over here. So better shift me this formula over somewhere here. Yes, I am shifting this formula over here. So it means that if I know the grip, so grip will be equal to the thickness of the both plates, and I'm using this A325 mm bolt whose diameter is equal to 25 mm, and I want to produce the 225 kilonewton pre-tensioning. So that I am computing by this formula because this is made of steel. So length of the grip I know, stress 225 megapascal, so kilonewton I need to multiply with exponent 3 also here. So here this stress value will be in kilonewton, so I need to multiply further by 1000 convert into the Newton. So only if I know the length of the grip, I need to know how much delta value I can provide. So what we supposed to do? We are stretching. We are stretching this board or try to elongate by providing this particular delta value. So if I am stretching this delta value, for example, this is coming out to be 2 millimeter. If I am stretching this by 2 millimeter, and after stretching, if I tightening it, the bolt, so material is in the elastic range. So what is happening? Material will tend to come back to its original position. It tend to contract. When it tend to contract, it means that it is providing the pre-tensioning or the compressive force to the both plate to tighten the connection. So next point arises that how I can monitor this delta value. For example, if I need to provide this delta as a 1.5 millimeter in order to produce a pre-tension 225 kilonewton. For this purpose, a special washers are used, which are called pre-tensioning washer, which are having protrusion or some humps or some deformation made on this top of the washer. And these are called as a tension indicator washers. So for example, the total height is equal to 1.5 millimeter. It is 1.5. It means that when I am tightening this bolt, so this material, which is this humps or deformation, they are actually, they will be deformed. So their distance will decrease. If total thickness equal to 3 millimeter, and I want to produce this much strain value or delta value in order to obtain pre-tensioning. So this delta is 1.5. So when I am tightening, I will monitor the distance between these washers. And when the length or the thickness of this washer is reduced by 1.5 millimeter, it means that I have provided it deformation as a 1.5 millimeter. And corresponding to this deformation 1.5 millimeter, I have provided pre-tensioning of 225. So what does mean? I am providing the strain, which is the function of the deformation and the length of the grip. And I know the E value of the steel. So indirectly, I want to determine how much deformation I need to provide in the bolt to produce some pre-tensioning. Because when I am reducing these thicknesses, so bolt tend to stretch. This bolt tend to stretch. And after stretching, if I will tighten the bolt, so the bolt material will tend to come back to its original position, so which is providing the compressive force on the plate, or which is providing a high contact pressure, which is protecting the plate to slip in the later direction. So this was the case. So this is the type of the forces if I am providing the strains in the bolt, and this is how the pre-tensioning is increasing. You don't need to memorize this case, you just need to understand the basic philosophy. So washer with protrusion or the gaps are used. Protrusion they flatten as bolt is tightened, and by the visual inspection we ensure that how much tightening we have obtained or how much gap is closed by the flattening of protrusion. So this table I have already explained. So typical type of the bolt joints, I will just maybe cover until here. So this is the type of the bolted connection that we may provide. We are connecting two plates with the butt joint, and we are providing bolts or the rivet in two rows. In each line, we are having 6 bolts, and at any cross section, we are having 2 bolts. These are the truss connection with bolt. This is the bottom part, we are having 3 bolts. This is the diagonal, we are connecting this with the gusset plate with the 2 fasteners, this vertical member with this 3 fasteners. So we need to compute the number of the fasteners required to transfer the forces from the one member to the gusset plate and vice versa. In case of the bracket, we are connecting the gusset plate with the fastener with the flanges, and they are provided in 2 rows. In case of the simple shear connection, we are using angle section to connect the web of the girder with the flanges of column. So bolted connection, this here, in this case, these bolts, they are subjected to shear. And here we are having different type of the bolted connection. So next time we will start from here, and we will see that what type of these stresses are acting in the fastener. So if you are having any question at the moment, you can ask me. So please raise the hand who are present. The students who are present, please raise the hand. So total they are 40 students, they are present, but I want to check the students which are absent. So so Anis Malik, where is there? Anis Malik, can you hear me? Anis Malik. So CR, please note down these students and text me their.
Okay, sir.
मैं अभी नाम एक अनीस मलिक, मैं इसकी पिक्चर भी खींच रहा हूँ यहाँ पे, ठीक है. एंड सेकंड इज आकिब अली. Aqib Ali. Aqib Ali is also not there. And Haris Chaudhary. Haris Chaudhary, he is also not there. And Miss Laiba, are you there? Please raise the hand. So Miss Laiba is also not there. And Anis Malik, where you were? You just joined?
सर मेरा ना नो सर मेरा मोबाइल हैंग कर रहा था
अच्छा चलो ठीक मैंने आज क्या पढ़ाया अनीस what topic I taught today?
मोबाइल के रिलेटेड
अच्छा अच्छा इस रिवेटेड कनेक्शन में कौन से स्ट्रेसेस प्रोड्यूस होते हैं?
एवरीबॉडी
बेरिंग फेलियर क्या होता है? बेरिंग स्ट्रेसेस and Umar Malik, are you there? Umar Malik, so please note down the roll number of
Yes.
Umar Malik.
Yes sir. Yes sir.
यार हाथ रेज करो क्या?
सर मैंने रेज किया हुआ ना।
तो यार अपने ये बटन दबाना। अच्छा नहीं नजर नहीं आ रहा, चलो ठीक है। ये हारिस चौधरी और आकिब अली, दे आर नॉट प्रेजेंट। ठीक है सियार?
Okay sir.
I will conclude the lecture. So if you are having any question, you can send me your queries. So till then, Allah Hafiz.